Taking some moments. Okay, we are live. So, good afternoon, good morning, good day to all watching this video interview. My name is Antonio Elias Salum Salazar. I am president of the Fundación Horacio Ducharne, and today I am glad to have with me Dr. Michele Mosca, an expert on the field of the quantum computing and artificial intelligence. Two things or two items which are very interesting for the work that we do at the Fundación Horacio Ducharne, because we believe these two items, these two aspects of the technology are going to play a very important role in the future of the cities. And since Fundación Horacio Ducharne is busy trying to develop a theory about cities, we believe that quantum computing and artificial intelligence play an important role to understand how cities will operate and will be in the future. So let me introduce our guest, Dr. Michele Mosca. I have here the resume he kindly sent me. I just go through it to present him. Dr. Michele Mosca is co-founder of the Institute for Quantum Computing at the University of Waterloo, a professor in the Department of Combinatorics and Optimization of the Faculty of Mathematics, and a founding member of Waterloo's Perimeter Institute for Theoretical Physics. He is co-founder and CEO of the quantum-safe cybersecurity company, Evolution Q, and co-founder of the quantum software and applications company, Software Q. He serves as co-chair of the board of Quantum Industry Canada. He started working in cryptography during his undergraduate studies and obtained his doctorate in mathematics in 1999 from the University of Oxford on the topic of quantum computer algorithm. His research interests include algorithms and software for quantum computers and cryptography tools designed to be safe against quantum technologies. He co-founded the not-for-profit Quantum Safe Canada and the ETSI IQC workshop series in quantum safe cryptography, and is globally recognized for his drive to help academy, industry, and government prepare our cyber systems to be safe in an era with quantum computers. Dr. Mosca awards and honors include 2010 Canada's Top 40 Under 40, Queen Elizabeth II Diamond Jubilee Medal 2013, SGU French Norm Schwartz Lifetime Achievement Award 2017, and a Knighthood Cavalier in the Order of Merit of the Italian Republic 2018. So a very wonderful and long resume. Welcome, Dr. Mosca. I am happy, glad to have you here. How do you feel?
Well, thanks so much. It's really a great pleasure to be here. Even greater pleasure to be in there in person, but of course. But I'm glad I have the opportunity to connect.
Perhaps next year, when the pandemic is over, we can meet together physically. Okay. So, Dr. Mosca, let me then start asking you some questions about a paper you wrote in the early few months ago. I think I have here the paper. Let me put this in the screen so we can have the same. Let me see if I have the opportunity. I believe I am just looking the, let me see, where is the paper that I wanted to show with our colleagues. Let me see if I have, I think it's not yet. Me share again, trying to share again, share screen, application, here we are, okay? I hope you can see the paper, Cybersecurity in an Era with Quantum Computers will we be ready? This very interesting paper that Dr. Mosca wrote recently. So he is asking about this readiness for the coming arrival of the quantum computers and how they are going to affect our life. Are you still here, Dr. Mosca? Can you hear me? Can you see the paper?
Okay. Yes, I'm
Okay.
still here.
Yeah, so in this paper, Dr. Mosca is making some statements about the risk that we are facing in the coming future, in the few months, I believe, when quantum computers will be more advanced, and how this advancement can break the current cryptography to protect data that we are used to use. To this risk, or to face and prevent this risk, Dr. Mosca recommends or advise to start working on developing new algorithms or new methods of cryptography. He calls them quantum cryptography and post-quantum cryptography. Perhaps, Dr. Mosca, for the sake of some of our audience members, can you distinguish, can you make the difference between these two solutions you propose for the quantum computers? What is the difference between the quantum cryptography and the post-quantum cryptography?
Yes, I'm happy to. And sorry, I'll occasionally turn off my camera. There's some bandwidth issues with one of the major telco network providers up here in Canada. And I didn't invent these notions or terms. In fact, we coined a new term called quantum safe cryptography to capture both of these families of solutions. The first family of solutions, which Dan Bernstein and others coined post-quantum cryptography, that's really the intention there is classical or mathematical codes you can implement with conventional classical computing technology, but that are designed to resist attacks by quantum computers. So a bit of a David versus Goliath type situation where we're only going to use classical technology to defend, but we're going to be secure against even quantum computers. There's mathematical assumptions, very much like the mathematical assumptions underlying RSA cryptography or Diffie-Hellman cryptography, or rely on something like the factorization of large integers into its prime factors being difficult.
RSA is one common use in this matters.
Yeah, by Revest, Shamir, and Edelman. So if factoring is hard, we have this very elegant method for authenticating, providing digital signatures, establishing secret keys on the internet and elsewhere. Of course, a quantum computer will break factoring will break RSA. It'll also break the alternatives based on Diffie-Hellman, the Diffie-Hellman protocol. So we have a big problem because since the 1990s, we knew in theory these protocols are broken, but they weren't broken in practice. So we continued to develop more and more digital platforms, and basically every critical infrastructure around the world directly or indirectly depends on these protocols being secure. Except quantum computers are coming. They're getting closer and closer. My own estimates would say around a 1% chance, between 1 and 5% chance that these codes are broken in around 5 years, probably a 20% chance they're broken within 10 years, right? And a much higher chance, around 50% chance in 13, 14 years. And we've surveyed many experts, and they have, varying opinions, but my opinion is roughly middle of the pool of opinions of experts. So we have to replace these codes with something. The obvious thing, not easy, but the natural thing to do is find new mathematical problems on which to base, cryptography, key agreement, and signatures. But it's hard because you need a sort of trapdoor predicate, which is what it's called in mathematics and cryptography. There aren't too many mathematical objects, mathematical tools that have the property that let you establish a key. Signatures is a bit easier. With signatures, you really need just a good one-way function or a hash function. But focusing on the problem of like HTTPS, there's a key agreement which establishes a secret key, and then you encrypt it with something like AES using that key. But how do you do the key agreement through an untrusted but authentic channel? Well, you need something like RSA. And there's about 4 families of algorithms, one based on lattice problems, one based on decoding error correcting codes, another based on multivariate functions, and another based on elliptic curve isogenies. And people are working on them for many years now, actually. The NIST, National Institute of Standards and Technology in the United States, is, I think, the foremost authority in the standardization of these kinds of algorithms, and they will produce the first generation of standards around 2023, 24. So it's been a long road. We started about 8 years before that. Around 2016 is when they started. Well, that's when they officially started. They were preparing years before that as well. So you see the long road to prepare. So we're going to prepare these new mathematical algorithms. There's also signatures. There's a version that's a bit easier. You can use a similar mathematical problems or even more robust problems like a secure hash function. The reason I'm focusing on key agreement is because quantum key distribution is really a key agreement algorithm. So it doesn't replace the other tools. It's an alternative for RSA and Diffie-Hellman key agreement or post-quantum key agreement. And it's not trying to compete on efficiency or cost, right? It's much more cryptographically secure, because with these new mathematical algorithms, like based on lattice, the hardness of finding short vectors in a lattice, there's always a risk that somebody finds a way to find short vectors in a lattice to break these codes better than we thought was possible. And we have to live with that risk, right? Quantum cryptography, there's no mathematical cryptanalysis possible. It's what's known as information theoretically secure cryptography. So any adversary watching the traffic, the information go back and forth, they don't have enough information to determine your key. But with post-quantum cryptography, if they had unlimited amount of time and computing power, they could eventually find the key. But right now, we think it would take thousands and thousands of years to find the key. But maybe we're wrong, right? We've seen it before where we thought it would take thousands of years, but then there's a mathematical advance and suddenly it takes a month or a day or a minute. Now, when you look at all the digital systems out there, I put them in a pyramid. At the top are the ones where we can't take that risk. I can't take a 1% chance or 5% chance that this is broken, because then society falls apart, right? Our country might collapse, or very bad things could happen if these codes are broken. The bottom of the pyramid, sorry?
No, it's life importance.
Yeah. System critical, mission critical, most critical assets here. The bottom of the pyramid, 1% chance, maybe I can accept that risk, right? Like this morning, the internet went, one of the major telcos in Canada has been having intermittent internet access. Doesn't happen very often, but every few years, this sort of thing happens. It's a risk we can accept, right? It's a nuisance, but life goes on. I might miss a meeting here or there, but it's not going to collapse the energy grid for a sustained way. But the thing with cryptography is we do have to be careful, because we're seeing cyber attacks all the time. Ransomware.
Dr. Mosca, where do you put the bank transaction in that pyramid? In which part of the pyramid put the electronic bank?
It partly depends on which banking system, right? If it's really just one credit card transaction, maybe it's below the line. But if we're talking about the entire financial system collapsing, or our confidence in the financial system collapsing, that to me is above the line, right? So there might be some pieces where, like, maybe I can't use the ATM for, the automatic, the cash machine for a day or a week. Okay, I can live with that. But if the financial system systemically, again, it's one thing for one bank to go down, but if all the banks go down all around the world for a month, we have a real problem, right? And if it's more than a month, even worse. So it's I would say the most critical parts of the financial system are above the line. But
most of these systems are working with RSA and with very long keys. I think the most important defense they have is to use very long keys, more than the algorithm. So I believe they use keys long more than 2,000 bits or something like that.
Yet nowadays, a typical configuration is RSA 2048 to do the
2048.
key agreement. So it's 2048-bit keys. And then at AES 256 for the encryption.
And the quantum computer can break that key in a brute force way in few minutes.
Yeah, it can break the not the AES encryption, AES 256. We don't know how to break it with a quantum computer. We can weaken it, but it's still super strong. But the RSA is broken. You can go to a bigger key, but you're not going to gain too much. I mean, right now.
But it depends also on the qubits of your quantum computer. I believe more qubits, easier it will be the breaking the key. I suppose.
Well, once it's a fun.
Right now, what is your assessment about the qubits for the quantum computer? So now we have talking about 100 qubits or more or less than that.
So right now we have about 150 to 100 physical qubits. A few hundred or thousand of those will create one logical, fault-tolerant logical qubit, just one. And then we need about 4,000 of those. So with various optimizations and so on, people think a few tens of millions, right now, we can improve this further, but right now, a few tens of millions of qubits running for a few hours can break RSA. But I have no doubt that within 1 year, 2 year, 5 years, we'll find even faster, smaller ways to do it. But it's still a large
24/8 bits long key. 24/8 bits long key.
Yeah, would require tens of millions of physical qubits. Now, I think we can maybe get it down to a few million physical qubits. Maybe if we're really lucky, a few 100,000 physical. But this is, we don't know. What's sufficient is about 4,000 logical qubits. And the size of a logical qubit, so one logical qubit is many physical qubits. How many? Well, that depends on a lot of things. Could be a few hundred, could be a few thousand. Depends on the error rate and a number of architecture issues. And we're constantly reassessing this assumption. But IBM said they would have 1 to 10 logical qubits by 2023. And my company's own surveys of experts all around the world suggest that that's a reasonable likelihood, that we could have fault tolerant a few logical qubits within 2 to 3 years. How long will it take to get 4,000? 5 years, 10 years? We don't know for sure, but I wouldn't assume, given what's at stake, we can't assume it's going to take a long time, right? So we have to be ready. There's no downside really to being ready. So we need to be ready for this possibility and deploy new and better cryptography to protect all of our digital systems right now. Now, with this, where we can't accept the risk, because we deploy new cryptography, but then if I come up with a new mathematical advance, it could be broken again, right? So we need, for the most critical systems, for the backbones of these networks and so on, quantum cryptography can help protect them in a way where we don't have to worry about mathematical cryptanalysis.
I see. Okay. So, but when I look at the architecture of this quantum computer, something that is shocking me is the lack of memory. So it seems that you can do the calculation without memory. It's not like the traditional architecture of a computer where you have the RAM, the ROM, the hard disk. So in a quantum computer, it seems like you have the qubits or the gates in a sequential operation. You don't need to use memories. Is that right, doctor?
Well, it's a good point, because the models, the way the computational model we define for quantum computing looks exactly like that, right? It's just kind of ephemerally flowing through, we have a circuit flowing through time. You prepare the qubits and they fly through the circuit. They go through gates and do the logic and so on. At the end, you get the answer. That's the model, the abstract model. And there are some people trying to implement something that closely resembles that, using photons as qubits, and they either send the photons through free space or through fibers or through integrated photonics. So there is one way to try to build a quantum computer that is more or less like you're saying. But there still is a notion of memory, but it's a very short-lived memory.
But the two-day architecture of the quantum computer has no memory.
So that I'm distinguishing the model from the physical architectures. So there is one physical architecture that resembles the model. the one you're describing. But the most promising physical implementations actually do have memory. The qubits are fixed usually in a 1 or 2D lattice, and the circuits are really describing flow through time, right? So usually it's one-dimensional array of bits flowing through, because that way you can draw it on a page or a PowerPoint slide, right? But it's really a two-dimensional grid usually, and it's flowing through time. So it's not flowing through space, because usually in the circuit diagram, it looks like the information is flowing through space. And again, with photonic quantum computers, they would be flowing through space. But with the superconducting circuits, they're really sitting on a chip. They're stationary, and we shine, radio frequency, microwaves, lasers, whatever, depending on the frequency of the qubits. So we shine up, we do transitions on the qubits, but they're pretty stationary on a chip of some sort. So, and again, the model is really conceptually that it's the flow of these bits through time. But they are we still have not yet evolved, but we will eventually have, computation qubits like our RAM, other qubits that are more for storage, right? Other qubits that are photonic qubits probably for communicating and interconnecting. We're still building these different kinds of qubits and different interconnections and converters between them. But the bigger there's a lot of focus on that to build a quantum internet. But for a quantum computer, the current focus is largely on building robust stationary qubits. Again, with the exception of the photonic approach, which is also looking reasonably promising. There's several companies pursuing it, but most of the players are looking at superconducting qubits, which are stationary, ion-trapped quantum computers, which are more or less stationary. They're ions floating on a chip, or spin-based, various kinds of spin-based qubits, which again are typically some sort of solid-state system. So they're pretty stationary quantum bits.
Yeah, I am asking because I suppose it's important also the hardware or the architecture when you want to standardize the cryptography, because an algorithm must work under certain assumption of the hardware in which he's gonna run. So when you standardize an algorithm, quantum cryptography or post-quantum cryptography, I suppose you need to establish or to fix above which architecture, which platform you are going to run these algorithms.
Yes, and so for post-quantum algorithms, it's purely classical architecture. So it's really the same as we've done before. The standards are really at the high level of the algorithmic standards. The transport layer, that's all stays the same. But it's at the various layers where the software is being implemented, or the hardware validation where things change. But it's all classical. QKD, indeed, it's still right now one of the challenges of QKD. It's still a very custom, proprietary. These two QKD boxes talk to each other with one set of wavelengths, one wavelength of photons, different. The equipment isn't interoperable. In fact, some of my work and my company's work is to do a software overlay on top of these heterogeneous point-to-point quantum cryptography links. So to the end user, it really looks like a ubiquitous common platform, because at the very bottom, it isn't. But the truth of the matter is, at the very bottom of our classical telecommunications infrastructure, we have copper, we have fiber, we have wireless, right? And I don't know if the bits going from here to Venezuela they're going through copper, they're going through everything and switching back and forth, right? It's all invisible to me. To me, it's just zeros and ones that reappear on your screen. We're not at that point yet, but our software overlay at least simulates that. It takes this heterogeneous collection of physical platforms and has one common classical computer interface with users, whether they're implementing TLS or IPsec or whatever they're doing with these keys.
It is also possible to combine quantum computer with classical computers. Do you believe that?
Yeah, I mean, in the short term, quantum computers are really a very special purpose, peripheral device you could think of. Most of our today's computer has many different kinds of memory, right? We have graphics cards, we have storage memory, we have computation memory, we have cache, like all sorts of different embodiments of bits depending on what we're trying to do with the bits. And quantum will be another one. You really only want to use a quantum computer if there's some massive algorithmic advantage to using a quantum computer. In the very short term, it's you through the cloud or through some internet connection, you send your problem and you get the answer back, right? Within some large data room, it might be more integrated with the classical computing platform. But it's really integrated as a part of a broader, classical computing platform right now. And indeed, at some point, you want to start to standardize these various interface, within the quantum computer, but also how the quantum computer connects with classical computers. Now, eventually, right now it's, quantum networks are really point-to-point links with classical connections, trusted nodes or something in between them. We are moving toward a quantum internet where we'll have quantum routers and so on. And we'll slowly start to rebuild the kinds of standards and interfaces you're talking about at the physical layer as well as the very software layers up to the application layer. So it's still very much a work in progress, but that's definitely the vision for the many colleagues around the world who are working toward a so-called quantum internet.
Well, one thing that I see, Dr. Mosca, is that we're going fast with this new technology, the quantum technology and the quantum logic. But since I work at the university, I don't see the same speed on the education side. I mean, still, I see the schools, the teachers are working with the classical concept of physics and the classical concept of logic, despite the fact that we know that those laws or those logics are not applicable or correct for the many things in nature. Why do you think that this difference in speed or difference in the logic and the handling of the physics between the schools at the university and the technology industry? Why is that difference?
That's a great point. It is.
They don't believe you. They don't believe on quantum logic, on quantum physics.
I don't know if it's a matter of belief or not. So, it started off, this was a niche area in a small number of universities around the world and a few industry labs. Now it's many universities. A large number of universities do it at the graduate level, and many are starting to do something at the undergraduate level. But, I felt over a decade ago, this is something that even a 15 or 16-year-old student can understand. And so why is this not in high school? So it is starting to permeate into undergraduate, largely because young people are asking for it.
No, they continue to study the Newton's law, the Newton law.
Well, so in a sense, like even at university, you mean?
No, in high school.
In high school. So I remember when I studied quantum physics in high school, and it didn't make any sense to me. So I totally agree. So in fact, and we need to do what we can to make it easy for high schools to introduce, this new curriculum to young people because they're ready for it. There's no reason they can't be exposed to it. So Perimeter Institute has prepared some, for teachers who want to go beyond the call of duty, there's materials they can use. In fact,
I don't know that in your paper you're looking for new photographers, people thinking. So it means that you need other kind of persons to prepare at the school. So some with a different logic. It's not wise to teach them the classical physics and the classical logic and then pretend they start to rethink in the quantum logic.
Yeah, I think, you have to learn some amount of classical physics before you can learn quantum physics. I think Richard Feynman once said, physics education is just one series of one lie after another, right? You tell the students one fable, and then you say, okay, you understand that? And they're like, yes, okay, that wasn't exactly true. Let me tell you a little bit more of the truth. So, at some point you need to simplify things, get some concepts across, and then keep building on this. So, quantum mechanics, quantum physics, grew on top of classical physics. And I think we can reinvent the path to what we understand today. We don't need to go through the long roundabout path, right? I think there is a shortcut, which I think is what you're really asking for. So we can't completely we have to do mv squared, all the basic physics, and then we say, okay, now here's a quantum mechanical framework. I do, and I'm biased, but I agree with you. There's a better way to introduce quantum physics than we currently do, which is largely historical. And so we start with these very complicated examples, and quantum physics looks much more complicated than it really needs to. And I think, and we started a school. I started it with 2 students, and then we grew it to 20, and now it's, I forget, dozens of students from all around the world come to Waterloo. Now they're doing it virtually because of the pandemic, and we teach them quantum cryptography. And they learn about qubits and all the basics of, and as you learn about qubits, you're effectively learning the framework of quantum mechanics. And once you understand the framework of quantum mechanics on simple systems, like these 0 and 2 state systems, now when I go generalize to the hydrogen atom with much more complicated state spaces, at least I understand the intuition. The analogy I like to use is when we teach probability theory to our young students, we don't start with complicated continuous state spaces. We start with a coin, right? One coin with 0, heads or tails, or 2 coins, or a 6-sided dice. And you learn things like Bayes' theorem, conditional probabilities, and so on. And then in 3rd year university, you say, okay, now let's talk about measure spaces and, integrating, and then sigma algebra. You do the more complicated probability theory. But by that time, I already kind of understand what's going on. I now understand Bayes' theorem. So instead of a sum, I put an integral. Okay. But you don't start with the integral and in the complicated systems, right? So I think, and quantum computing is probably the simplest platform in which to introduce the quantum paradigm for physics. And I'm obviously biased, but I feel pretty strong that really is, the best way. And eventually that will be how the education system introduces quantum theory. And I agree with you. We should start introducing it to our young people in high schools.
I suppose also the programmers to program a quantum computer is not the same as a classical computer. So
well,
it change something in your mind.
Well,
so can you still apply object-oriented paradigm?
So you have to start with classical programming, and then you add on the quantum piece, right? So you don't start in grade school with programming qubits. You start with the basic elements of computer programming, and then at some point you can again in high school there's no reason you can't be introduced to very elementary quantum programming. But I do think you need some of the basic classical foundation, and then you can build on that to understand how to program quantum computers.
For instance, there where you are in Canada, in your opinion, are they taking seriously the teaching of the quantum logic, quantum physics at the right level, or are they still conservative, or prefer to keep teaching too much classical physics, classical logic?
I don't want to criticize. I think the education system, it's complicated, and there's a lot of politics, as well as resource constraints. So I don't want to criticize them, but I think the bottom line, and I don't actually know how far they've gone. Like I said, there's teachers all across Canada and the world, actually, who come to Waterloo to learn these cutting edge areas of physics and how to teach it to their own students. And then they go back to their country and their city, and they, on top of the normal curriculum, they do teach some of these extra pieces. It would be good if this eventually became part of the standard curriculum. But I take an evolutionary approach, and there's maybe some outdated, if you put more in, you have to take something out, right? So you do have to think this through carefully. Unfortunately, this often gets politicized, and I don't know how it works in other parts of the world, but a new government comes in, and often they'll want to revamp the whole education system, and then 4 or 8 years later, the next government tries to do the same thing. It can be a bit disruptive to the curriculum that way. So it's a bit it's a bit politicized, which is unfortunate, because it's fundamental to the success of our countries and societies that we really educate our children in the best way we can. I'm not saying it's completely political. I mean, they do try. They are, when they do these things, they do it for the right. They are trying to make things better, but it can often go yo-yo back and forth. But I think it would be good if, as we oscillated through these different curriculum changes, we did integrate a bit more of quantum ideas at an appropriate level for high school students. So when they show up in high school, this is all normal stuff. They can do the more complicated version, but they're not, this idea of superposition is normal to them. There's no reason you can't do that in high. In fact, we have introduced it both at Perimeter. We do a summer school for high school students in physics, mostly quantum, and at the IQC, we do this quantum cryptography summer school for grade 10, 11, 12, so 15, 16, 17-year-old students. And it's open to students all around the world.
Yeah, I suppose when the industry pushes for changes, because there are quantum computer, quantum internet, quantum programming, they are going to ask those changes in the education system. So they will have to adapt to this new reality.
Yeah, and I'm not an expert on, the political what kind of pressure eventually leads to these kinds of updates to the education system. I mean, they're certainly always under pressure to add more things. And like I said, to put new things in, you have to take some things out, and you need teachers who are able to teach these new things. So, but I do think we need to be strategic for the sake of our young people and the sake of our economies and our countries, and get better at modernizing the education system. Again, not to suggest it's easy, but I think we do have to get better at that. And there's a lot of technology that can enable it. Like you can now rely on videos available online, right? You can watch experiments that other people have done online. It's so much easier to share pedagogical material nowadays. Bring in a guest lecturer like I'm here from the other, thousands of kilometers away. So I think we can do that better going forward. It is a challenge, and I totally agree. We should be integrating more of the conception, more of the basic elements of quantum mechanics and quantum information at the high school level as well. Because look, if you don't, your students, your young people are going to be disadvantaged in the global marketplace, whether it's the education marketplace or the job market or commercialization. I think you do want your young people up to speed, on par with other children all around the world, and understanding these. Look, when I was very fortunate, my family's from Italy, but I grew up, I'm from Canada. I was exposed to computers at a very young age. I was programming computers. My family in Italy, my cousins, they'd maybe seen a computer once, right? Yeah. They didn't know how to program. So I think they had a disadvantage to me in Canada. So I think it's really important to, as much as possible, at least get the concepts across. And with cloud, you can access quantum computing platforms or good simulators for free on the internet. Yeah. Like we developed an open source quantum computing simulator. So actually, for high school level, even undergrad level, that's probably enough, right? To understand how to program a quantum computer. Of course, you have to understand what a quantum computer is before you can program it. But these are all, currently available to students anywhere in the world.
Yeah, is there a quantum computer simulator in the Waterloo University, Dr. Mosca? Because I know that IBM has one, but I don't know if other actors are.
Yes, called Quantum Plus Plus.
Quantum Plus Plus. Yeah. Okay.
If you look for Google or do a search for Quantum Plus Plus, you'll find a free simulator. It's better than all these other ones, in our unbiased opinion. It can run on a lot of these other simulators. They have access to very intense supercomputing power. Ours will simulate 25 or more qubits on a PC, so which is pretty impressive. So look, I mean, of course, I'm joking. Well, actually, our benchmarks indicate it really is the best simulator out there that's available freely and can run on a conventional platform. So we encourage people to use it, but there's other good ones as well, of course.
Okay, so thanks for that information. Now closing our interview, because it's almost more than half an hour that we are here talking. I wanted to touch one point about the standardization work, because I know you from the IEEE standardization work, and I wanted to ask about this effort to try to standardize from IEEE the quantum cryptography and the quantum computing. And does it make it's not better to have this standardization work, for instance, in another working group already established, like the 802 working group? So why not to try to connect the quantum computing efforts to standardize to the already existing working groups on IEEE, for instance, the 802?
Yeah, I mean, that's happening to a lot. It's still evolving, but I'm involved with many standards bodies. I'm most active with ETSI, European Telecommunication Standards Institute, which brought us GSM and many other of the leading mobile standards. I just recently helped co-organize an ITUT, which is another major standards body, and together with ETSI, workshop on this. This is on quantum safe cryptography, both as post-quantum and QKD. IEEE, I've participated in events where they're looking at risk management standards. So I've been strongly encouraging the different standards bodies and all the experts to work together, because like you said, some standards bodies like IETF designs the TLS standards, right? So we work with IETF for TLS. They cross-reference the NIST standards for post-quantum, and ETSI has its standards, and so on. And ITU, we don't duplicate; we cross-reference. There's liaison agreements.
Also, the Bluetooth standard interest system group, what do you call Bluetooth SIG, special interest group. The Bluetooth special interest group also is concerned about security in Bluetooth devices. So.
And like I volunteer, with X9. It's a financial standard out of the United States. So they refer to NIST standards, but they produce, important standards for the financial sector. So standards often build on each other. Like NIST might do the low-level standard for the algorithm, but then someone else will standardize how it works inside HTTPS, right? And so on. And so there's this complicated web of standards, and I think it's important that as we identify gaps, and they're filled. But again, we don't need to duplicate, but we do need. You're right. We still have many more standards that need to be developed as this field evolves. But like I said, the risk management, that's a whole other thing, right? Because we can have the technology, but if people don't prepare to make their systems resilient, it won't matter either, right? So we need us. But then why aren't people prepared for the quantum threat? It's not being managed as, in a standard way. They don't know how to manage it. It's a risk management problem. It's a new weird risk. They don't know how to they don't know how to manage it. Everybody's doing it differently. So if you had a standard, then it makes it easier, and it also makes it a more credible thing to do. So there we go. So I mean, they don't have these standards yet, but they're starting an effort to look at standards for how do you manage quantum risk, quantum related risk.
And I suppose also China is building his own standard for the quantum cryptography.
Yeah, and working alongside, so they're very active in ITUT and other global, participating, and they're also developing some domestic standards as well. So China is definitely very involved, both in the international standards as well as their own domestic standards.
I believe. Okay. So, well, I think we covered all the questions we have, and we really appreciate all the time and effort for being here, Dr. Mosca. It was a great pleasure to share with you this interesting subject and quite challenging issues that we are facing in the coming future. So, if you want to say some final words about the quantum computing, or some recommendation for the people watching this video, how to convince them to start thinking or to start applying quantum logic and not more classic logic.
Yeah, well, thanks so much for your interest and enthusiasm in this subject. We've tried very hard to make resources available for anyone in the world. So I just put in the chat openquantumsafe.org. That's a place where you can get robust, good implementations of post-quantum cryptography. So you don't have to develop it from scratch. You don't have to pay money for proprietary implementation. So it's something you can start experimenting with in your own systems, right? If you have an engineering or computer science course, you say, hey, I wonder if I can make this application quantum safe. You can already do it. If you want to experiment with how QKD would integrate in a real-world system, we have an open source platform for integrating QKD into real-world networks. And I've already pointed you
that is a good recommendation for the students of the course. I am going to put in an assignment about that.
Yeah, wonderful. So, we're trying to, make this and then, of course, contribute back and spread the word. This is a very exciting time to start working in the field of quantum information, because the devices are now starting to happen, are starting to be realized. It's still early days, but we can now start programming and planning. So it's a very exciting time to learn about this field.
Yeah. Well, let me then end the broadcast. Please don't go away, because I end the broadcast and we keep a few minutes continuing the conversation. Thanks everybody for watching this video. And of course, if you have questions and doubts about what say in this interview, feel free to contact me in the email provided in the comment area. Thanks a lot to Dr. Mosca, and we end the broadcast here.